Hey everyone, and welcome. Today, we're going to tackle something that's like a cornerstone of physics, the kinematic equations. Now, I know that sounds a little intense, but these are basically the super powerful formulas that let us describe and even predict the motion of pretty much everything. We're talking a thrown ball, a speeding car, you name it. So, let's get moving. So, picture this. It's a super simple everyday situation, right? A car at a red light, the light turns green. But how would you figure out the exact distance it travels in, say, 10 seconds? It's a real puzzle, isn't it? And I promise, by the time we're done here, you're going to have the exact tools to solve it. No guesswork needed.
Okay, so to even start answering that question, we've got to learn to speak the language of motion. And that means we need to get familiar with the basic variables that physicists use to describe how anything gets from point A to point B.
And it turns out that pretty much any motion where something is speeding up or slowing down at a steady rate, well, you can understand it completely with just 5 key pieces of information. So let's meet the team. All right, first up we have S for displacement. And here's the key thing you got to remember. This is not the same as distance. Think about it like this. If you run a full lap on a 400-meter track, you've run a distance of 400 meters, for sure. But because you ended up right back where you started, your displacement is a big, fat 0. It's all about how far you are from where you began.
Next on the list, we've got U for initial velocity. It's super simple. It's just how fast something is going and in what direction at the exact moment we start paying attention, when we hit the stopwatch. If it's starting from a dead stop, U is 0. If it's already moving, then U is whatever that speed is.
And hey, if you have a beginning, you've got to have an end, right? So V is our final velocity. It's the speed of that object right when we stop the stopwatch. It's the after picture to the before picture of U. Simple as that.
Now this is the one that makes things interesting. A is for acceleration. And listen, this is a big one. Acceleration isn't just about hitting the gas. If something is slowing down, it's also accelerating. It's just what we call negative acceleration. You might have heard it called deceleration. Really, it's any change in velocity. And finally, the last piece of the puzzle, and probably the easiest one, T for time. This is just how long did the whole thing take? The time on the clock from the start of the motion to the end. Okay, so we've met our 5 key players, S, U, V, A, and T. And this is where the magic really starts, when we see how they all connect. For that, we have this awesome toolkit of 5 equations. You'll sometimes hear them called the Suvat equations, which is just a handy way to remember the 5 variables.
So check out this table. Each equation is a different way to relate our variables. But here's the truly clever part. Look closely. Each equation uses 4 of the variables, but it always leaves one out. And that right there, that's the secret weapon for solving these problems. Your whole job is to figure out which piece of information you don't have and then pick the equation that doesn't use it.
Look, having a great toolkit is one thing, but if you don't know how to use it, it's not much good. So we're going to borrow a killer 4-step game plan, inspired by the problem-solving methods they teach at IT, to help us crush any kinematics problem we come across.
This is it. This is your roadmap. First up, you got to understand what's going on. What information are you given? What are they asking you to find? Sometimes drawing a little sketch actually helps. Second, you make a plan. Based on what you know and what you need, you pick the one perfect equation from your toolkit. Third, you execute. You plug in the numbers and you do the math. And finally, and don't skip this, you check your answer. Does it seem reasonable? Are the units right? It's a lifesaver.
All right, that's enough theory. Let's put this stuff to the test. We're going to grab our toolkit, use that 4-step game plan, and finally solve that car problem from the beginning.
Okay, so let's remind ourselves of the problem. We've got a car. It's stopped. The light turns green and it starts accelerating at a steady 5 meters per second squared. It does this for exactly 10 seconds. And our job? Figure out exactly how far it traveled.
All right, step 1, understand the situation. Let's list what we know. The problem says the car was stopped. Ding, ding, ding. That's a huge clue. It means our initial velocity, u, is 0. We're flat out given the acceleration, a, is 5, and the time, t, is 10. And what are we looking for? The distance, which is our displacement, s.
Okay, on to step 2, the plan. Let's look at what we have. U, A, T, and we need s. So which variable is the odd one out? The one we don't know and don't even need to find. It's v, the final velocity.
So we dive into our toolkit and pull out the one and only equation that doesn't have a v in it. See how that works? It's brilliant. Now for the fun part. Step 3, execute. We just plug our numbers into the formula we picked. Our initial velocity, u, is 0. So that whole first part, u times t, just disappears. It's 0. That makes things easy. So we're left with 1/2 times our acceleration of 5 times our time of 10 squared, which is 100. So we've got half of 5 times 100. That's half of 500, which is 250. And boom, there it is, 250 meters. That's our answer. But wait, we're not finished. Step 4, check your work. Does this make sense? Well, the units are in meters, which is a distance, so that's good. And 250 meters, yeah, that feels about right for a car accelerating for 10 seconds. So, check.
Okay, so you've seen how powerful this is, right? But it's also pretty easy to trip up if you're not careful. So let's talk about a few common pitfalls to watch out for. Knowing these will save you so much trouble down the line.
All right, probably the #1 mistake people make is getting u and v mixed up. They're both velocities, sure, but they tell completely different parts of the story. Just remember, u is the snapshot at the very beginning. V is the snapshot at the very end. You got to keep them separate in your head.
And here are a couple more pro tips to keep in your back pocket. If a problem uses words like at rest or dropped or stationary, that's code for u equals 0. If you see slowing down or braking, that's your signal that acceleration A has to be a negative number. And please, please always make sure your units are consistent before you even start plugging in numbers. So what's the big idea here? What should you really walk away with? It's this. With these 5 simple equations and that solid 4-step plan, you've unlocked the secret to analyzing the motion of anything that's moving with a steady acceleration. Think about it. From a tiny falling apple to a massive train hitting the brakes, the exact same physics applies. It's this incredible, universal toolkit for understanding our world.
So now you literally see the world differently. A little more like a physicist. You've got the tools to not just watch things move, but to describe it, predict it, understand it. So I'm leaving you with a little challenge. The next time you're out and you see something moving, a car, a bike, a ball being thrown, just pause for a second and think. How could I describe that? What would I need to know? Because now you know that the physics isn't just in some textbook. It's happening all around you all the time.